Yeah, so it's always a great pleasure to return to CIRM, and it's even greater pleasure to be at a conference in honor of Rick. He has motivated much of my research, and in particular this one. And I have somewhat, I wanted to come up with a longer title than the title of the conference, and I managed to do that. So the title was Coulomb, Gaussian lattice models, but I want to explain a little bit what I mean by that. So maybe we'll start with the lattice models. And there is something special about two-dimensional statistical physics. You really see universality more pronounced than in higher dimension, and you see beautiful exact solutions. And now I realize that I've heard about this area much before I met Rico. Later on, read his newspaper. When I was in school, there was this, we had this beautiful series of books in Soviet Union, which was called Library of Quantum magazine. And this one, you can test, if you don't know Cyrillic, you can test whether how far your knowledge of Greek gets you. So it's called Physics and Geometry of Disorder. So that's the first time I've heard about percolation, but then I forgot about it for a very long time. And here there are three pictures of three different phenomena, which are all SLE 8/3. Now, okay, and now we, okay, so, now it works. So what's so special about 2D? It's really, there is this magic. It's like in complex analysis, you can't really pinpoint to one fact. There are several things in this constellation which come together. Since 1940, since Kramers and Vanier, they were both in physics and math, some exact solutions to the models, and at the time all the people tell that Ansager's solution of Ising model came as a shock, because people suppose that if you have some non-analytic function, you can't write an exact formula for that. Of course, it's piecewise analytic. And then came Conformal Field Theory. So it was the breakthrough papers first by Polyakov and by Belavin, Polyakov and Zamolodchikov, and immediately Cardi worked it out with boundary conditions. And what I'll be speaking about came a little bit before the Nijs and Nienhuis, so it's not conformal field theory per se, but conformal invariance was implicit there. When I joined this area, many of us did, what was so striking is that you get this kind of crazy prediction that Hausdorff dimension of percolation cluster is 91/48. I never ever thought that I would be proving that something is trying to prove that something is equal to 91/48. Or that if you count lengths and simple curves on the lattice, then the number will grow like mu to the power n and to the power 11/32, where mu is lattice dependent. So the main term is lattice dependent, but the next term is kind of universal. And it all has some physical explanations in the sense, for example, here mu plays, you can think role of temperature. And temperature is not universal, like water and wine, they boil at different temperatures. But the way how they boil is sort of similar. So what was sort of interesting here, that you had all these beautiful numbers and there was beautiful algebraic geometric structure, but it was kind of detached from the lattice theory. And that was the bottleneck, how to understand, even to mathematicians, even the continuum counterpart of CFT was not exactly rigorous. It was sort of more algebraic than analytic, but the discrete was completely detached. And then many people in this room tried to understand and came up with some solutions. So there was this big breakthrough 25 some years ago, which first came with the Schramm-Lochner revolution, and there was beautiful work by Adet, and then Adet with Greg and Wendelin and Stefan Roy, and many people in this room. So if I list all the people in this room already, that won't be enough to put on the slide. And then on the other hand, we start trying to connect discrete models to the continuum, and the first work was Rick's paper on the conformal invariance of domino tilings, and then many more things came by Greg and Adet and Werner, Schramm and Werner, and myself with Dima, and then Adet and Scott, Schramm, Sheffield. And so we advanced much more in discrete complex geometry, but I say that by today sort of viewpoint, we are still the bottleneck is discrete versus continuum. Continuum I understand much better than we did 25 years ago, and there are fantastic papers, but still there is this thing. Now I want to say what I mean by lattice model. So what I will be speaking about in the end, it applies in fairly general settings, which splits in sort of three subgroups of related models. And one is a all-fan loop model, where you basically take a tiling by these triangles of 3 types, which should fit together. So it's like loops on hexagonal lattice. And there are 2 weights, x to the power length of the loops and n to the power number of loops. So this includes a lot of things, for example, critical percolation, critical Ising ferromagnet, self-avoiding walks if you choose n and x appropriately, and the whole other spectrum. And this model, so it's a simple tiling model. You have like 2 boxes of tiles, empty triangle, triangle with an arc, and then you tile and you count how many tilings are there with the weight. Even the case when n and x is equal to 1, both are equal to 1, then it's interesting because it's percolation on side percolation on triangle lattice. And this fits in a more general model which was proposed by Nienhuis, where you allowed not only triangles but also rhombi, and rhombi with the angle not necessarily equal to 60 degrees. So if it's 60 degrees, then you should just split into 2 triangles. And Nienhuis observed that there are very specific ways for which this model satisfies Young-Baxter relations, well, those are the weights. It's actually interesting because there are, I think we have a paper with Chilkak and Glasman with Dima and Sasha, who are both here. And I think it's the only paper where in writing they are done correctly without a typo, because these are complicated formulas. So Bernard has a typo, John Carney also has a typo. So it's, but actually I'm not sure we don't have a typo, but at least we have, sorry? Yeah, you trust Sasha. Okay, I also trust Sasha. Trust Sasha, trust Sas. Yeah, that's okay. But there is this magical things. And then John Cardy and Niklif, they observed that actually for this also you have this sort of half holomorphic fermions can be transferred from hex lattice to the general one. Now this example, if you take the angle of the rhombus to be 90 degrees, so it's symmetric weights, there is no difference between kind of a loop which goes on a short in an obtuse angle or in a sharp angle, then, for example, these are weights which would correspond to universality, some of the weights which correspond to universality class of percolation. So we don't count the loops, but you count these things. And then it has a, well, if you don't want connectivity, if you don't want the connectivity of loops, which does make much sense for percolation, but still you keep some observables, you can just join the last 2. So you have 4 tiles with weight 1 and 4 tiles with weight square root of 3/2. Okay, so this actually, it's a different thing which we are trying to do now just to show that converges by percolation in some sort of short way, but unfortunately there are difficulties because there is no FKG for this model. But the interesting thing, if you have 8 tiles, it's kind of logical that it should have bijection with 8 vertex model. So this actually, you can replace these tiles by these pictures, by this bijection. Basically, there is a arrow which points to the right if there is a blue line on the right. There is an arrow which points to the left if there is no blue light on the line on the left. And then you would just have a picture of arrows which fit together, so it's like a perfect flow of water where on the borderline of 2 tiles, some water comes in, some water comes out, and in each tile there are 2 arrows which come in, 2 arrows which come out, except for these 2 tiles on the left, this one. So this is a source, so this is where there is a fountain which goes into all 4 directions, and then there is a sink where the water disappears. So if you remove these 2, there will be the so-called 6 vertex model. So it's a perfect plumbing when there nothing disappears, just water flows forever. You can also do an interesting thing. You actually can forget not one column, but the first 7 ones, and just leave these 2 tiles. So this seems to be the sort of easiest model. You have 2 tiles. Actually, you have just 1 tile with 2 different positions, and you tile by it. And you count the configurations. If you don't have n to the power number of loops, already you get something non-trivial, because you can look at observables like whether these 2 points are connected. Look, I moved 1 tile, and they are connected. I removed it, they are not connected, so you can no longer arrive by loops. So already these things are interesting, and if it's weighted by n to the power number of loops, then you get many, many more interesting things. Again, and this is motivated, this is related by bijection with the Fortin-Castellan random cluster model. So there are these blue clusters or dual yellow clusters, and then you replace blue edge by one of the tiles yellow edged by another tile, and then you have this loop bijection, which works very well in the critical regime. If the regime is not critical, you have another type of weights, which depends on the adaptation of plaquette. So there is bijection with this model, which is not the subject of this talk, and that model, random clustering internals, has bijection with spin models like Ising model, so there is this whole lot of bijections. So I want to mention another model. So it's the square ice model, which was suggested by Linus Pauling. So this, his picture graduating from Caltech, and his picture explaining how you get polymers with spiral structure. So it hangs in the bar of Caltech. So if you want to get drunk on the picture of Linus Pauling, you can just go to Pasadena and do that. And he suggests this is a simple model for the residual entropy of water ice. So you think that the ice molecules, water molecules, they're just oxygen and two hydrogens at 90 degrees. And then you assume that it's a flat ice. Well, we know that it's not 90 degrees and normally don't have flat ice, but ironically, if you do like ice on the surface of graphene, it will be almost 90 degrees and it will look like that. So he didn't know that at the time. And then you just say that there are no two hydrogens on the same bond. So on every vertex, you have oxygen with two arms. There are 6 possible ways to put two arms if there are 4 directions, so 4 times 3 over 2. And then you count how many patterns are there. This is sort of the same thing as saying that you do a puzzle piece. So we had back then like 2 different puzzle pieces, so 8 different puzzle pieces. So here there are two different ones, and one comes with 2 rotations, another with 4 rotations, and you count them. It's a famous theorem of Elliott-Lieb from 1967 that it grows. It's an easy exercise if you're bored with the talk to show that, and you haven't seen this before, that A is small equal than 2 and big or equal than root of order 4 of 2. Slightly more complicated to show that there are strict inequalities. And Elliott-Lieb has shown that it's 8 over 3 square roots of 3. Actually, as far as I know, there are a few proofs, but I haven't seen a simple combinatorial proof, and I'm sure that there is one because this number doesn't look very scary. It's not like 91 over 48, so there might be some nice argument. Okay, so how does it look like if you have a random one? So here there are 6 different orientations, so you cover them in different colors. Well, it's not very explicative you just have some random abstract picture. But then comes this intuition which goes from dimers, and it was sort of public knowledge for Losange tilings, and similar thing, height function, was introduced for domino tilings, as far as I recall, by Thurston. So if you take a random tiling by Losanges and here with angles 60 and 120 degrees, and you cover them in 3 colors, then you sort of see a 3-dimensional picture. 90% of people see cubes in the corner of the room, and 10% see the opposite thing, that you remove something from the corner. So there is this beautiful work of Rick about that, basically there is this Con-Canyon probe paper which tells you what would be, if you take a random tiling, what would be the average height function. And then there is this work with Andre and later with Scott about how fluctuation should like, and still there are some important conjectures open there, though for hexagon we know very well. So the question, how do you do these height functions for the previous model? So here it's just given by our visual cortex, this height function. And this is fairly easy. Just instead of 6 puzzle pieces or 6 water molecules, you get these arrow configurations we had in the beginning. And you have an arrow configuration such that for every vertex there are 2 incoming, 2 outgoing. It's more or less like, well, you can say that it's in exact form, but you can also say that it's like geographical map, where when you pass an arrow, you climb 1 meter or go down 1 meter. And so it's a consistent map. So you have a height function which changes by 1 when you cross the arrow, depending whether the arrow goes left to right by plus minus 1. So you get a height function, and you can count just the number of tilings with weight 1. You can look at the random height function, but you can also put weights. So the traditional labeled A1, A2, B1, B2, C1, C2. And the regime we're interested in, first it has to be symmetric with respect to flips. But also we want critical models. So this is already interesting enough for us. 1, 1, 1, 1, CC, but whatever I say we actually applies for the other things. You should only skew the picture. Okay, and that also has, there are a bunch of other bijections. There is a bijection with dominoes where you basically, well, the bijection is just graphically represented there. So the unfortunate thing is that there is one picture which corresponds to two domino pictures. So there are squares where a square 2 by 2 you can cover by two dominoes horizontally or vertically. And in some cases that doesn't change the arrow picture. And what happens is that if you do dominoes with weights 1, 1, 1, 1, then you get this number, these 6 numbers, 1, 1, 1, 1, 2, but 2 for some vertices. And then basically this is related to Bernoulli's fermionic point and all that for 6 vertex mode. But in general, if you want to relate arbitrary C to this picture, you get interacting dimers where some plackets have different weight depending whether there are two dominoes or not. And otherwise, the talk would be trivial. Otherwise, we would have solved this 20 years ago. Okay, and there are many more bijections. So I stole a picture from Philippe's paper, and it's just like 6 of the bijections, 7 of the pictures, but there are many more. Actually, the interesting thing is that if you have hexagonal lattice, you can imagine it as cubes, and cubes you can rotate and look from the side, and you have squares. So there is this point that it's actually they're not that dissimilar. Okay, so that was about the statistical physics and what we want to describe. And then I want to say what is Coulomb gas. So it was introduced by Nijs and then picked up by Nienhuis in 1982, so 3 years before Belavin, Polyakov, Zamolodchikov paper. And I will try to describe basically the core of their argument. So their argument, it applies to all the 3 pictures I discussed, this Nienhuis model with loops on hex lattice, the FK model with the loops, or the 6 vertex model. So let's do the FK loop model, a picture like that, weighted by n to the power number of loops. And we should be careful about boundary conditions, so we can do it in the whole plane, large volume limit and all that, or we can do it on a torus, or we can just freeze the plackets which touch the boundary. So one thing which we want to ask before we proceed, how to make these weights local. Because, for example, in Ising model, the weights are local. To calculate weights of some domain, you only need to know configuration inside. But once we have n to the power number of loops, if n is not equal to 1, if I cover half of the picture, and you see, for example, 2 half loops, you don't know whether it's one loop, they might be related or not. So there is a trick due to Baxter, which works like that. So variant loops, and choose complex unitary number mu such that mu plus mu reciprocal is equal to n. So basically, what we do, if there are clockwise, counterclockwise loops, we weight them by mu. So for example, this picture has weight mu cubed because there are 3 loops. Each of them are oriented counterclockwise. Now, this picture has 2 counterclockwise weight mu, and then there is one here. There is one here which is clockwise direction, so it's mu times mu reciprocal, so the factors to mu. So weight of this picture is mu. So this works when n is between -2 and 2, because we want it to be the sum of mu and mu reciprocal, and we want mu to be a unitary number. It's actually kind of interesting because it's, well, it's not a reason why there are different phase transitions for n bigger than 2 and smaller than 2, but it's one of the possible ways to prove it, that if you try to write it with mu, then for n smaller than 2 you get unitary mu, for n bigger than 2 you get a real mu as a solution of this equation. Okay, now let's choose nu such that nu to the power 4 is equal to mu. And now we weight left terms by nu and right terms by nu reciprocal. So what happens when we go around some cycle? So if you go around the cycle, because of planarity, the total winding of the cycle will be either plus 360 degrees or minus 360 degrees, depending on whether it's clockwise or counterclockwise. So each time when you turn right and then left, you cancel out nu and nu inverse. So for counterclockwise, you will have a net product of nu to the power 4. For clockwise, net product of nu to the power -4, mu inverse and mu. So basically, what we did is that we made the weights local, so it's a big thing. They give us this complex Baxter model with complex loops. But if we forget orientation of the loops, then we just get the usual model with loops with weight per loop mu plus mu inverse. And the other bonus is because we have oriented the loops, it looks like a geographical map. You see, geographical map, you have loops, well, the Lebesgue curves where you have the same altitude with respect to the sea, well, drawn every 100 meters or every 10 meters. But unless you orient them, you don't know whether it's Mont Blanc or it's a Mariana Trench. So you need to orient them and then have height function h. So there are two positive things in red. But if you have two positive things in red, you should have two negative things in blue. So the two negative things are the weight are complex numbers. And the other, that the measure is no longer probability measure because of that. So if you project this measure on the usual one, the total mass is 1. So the total mass of your measure is 1. But there are many cancellations when you project. And if you do large volume limit, you will see that total really mass with absolute value blows up. The thing that the weights are complex, it's not really a bad thing because I'm complex analyst by education, so I like complex numbers. So and also it's something which allows you to do more interesting things. Okay, now we have local weights due to this Baxter thing. And then instead of 2 puzzle pieces, we have now 8 puzzle pieces which look like that because we oriented the loop. So these are 8 possibilities. So let's calculate their weights. It's a very nice exercise if you haven't done this before. So there are left turns which go nu, right turns which go nu inverse. And then what you see that the top row, you always have one left turn and one right turn. So you take a product is 1, and the weights are real. In the bottom turn, no, you have 2 left turns, 2 right turns. But then there is another projection. You can notice that these 2 pictures, if you don't care how the water is mixed inside this square in this placket, there are 2 incoming from left and right and outgoing up and down. So from the point of view not of a plumber who is fixing the plumbing, but a person who uses plumbing in this apartment, they are exactly the same. Water is coming from east and west and going to north and south. And if you make a sum, the sum will be a real number. That's the place where we want nu to be a unitary number because we want nu squared plus nu to the power minus 2 to be a real number. So nu has to be the real, but then it's a different story, or unitary. And if we denote this by C, then we get exactly the 6 vertex model, 1, 1, 1, 1, 1, CC, so exactly the one which I described and with real weights. So it's kind of an interesting thing because we started with the unoriented loops, put orientation, got complex weights, then we projected in an arrow model, again real weights. It would be actually very nice if not for different boundary conditions working well with these 2 different models. So the boundary conditions which work well for both of them are very, very rare. And so this is one of the things which makes this complicated. Okay, so those are the height functions. And then if you observe the height function, then in the first 4 cases, the height function has a linear slope. So it's like -1, 0, 0, 1. And in the last 2 cases, it's a saddle height function. So basically, the weight, whether it's 1 or C, depends only on the gradient of the height function. At a saddle point, it's C. It's a flat point, it's 1. So this was the original argument of the Nijs and Nienhuis in a nutshell, that you have a random height function on a lattice. Weights depend only on gradient of this Hahn function. Let's pass to a limit. Well, we all believe that there will be a limit by, well, of course, by compactness, there will be subsequential limit, but we believe then we live in fairly nice world, so the limit will be there. And then the probability also of a given height function should depend only on the gradient of the height function in the limit. And it should be rotationally invariant, so there should be no term like gradient. It should start with gradient squared. And what is the simplest function which is rotationally invariant depends only on gradient squared. It's just gradient squared. And in principle, you can have a hand-waving argument why there are no next terms, because we only operate with a placket with a height at 4 points. And if you calculate height at 4 points, you cannot get anything more complicated than gradient squared. You can get Laplacian from 4 points, but you cannot get bi-Laplacian. There are too few points to do discrete approximation. So maybe a few remarks are due. First, this thing is a random distribution, not a function. So this picture I didn't write. I think it's stolen from Scott. So I keep stealing pictures from people in the room. So it's so whenever the picture is stolen from someone in the room, I don't attribute it. And I presume that Akunykov is in the room. Yeah. Okay. So the second is that Gaussian free field. So this is the definition of what people call a free boson or a Gaussian free field. It's known to be conformally invariant. So basically, it's a Gaussian field whose correlations are given by Green's function of Laplacian. Laplacian is conformally invariant in the plane, so the whole thing is conformally invariant. And how does this work? There is a parameter there which is denoted by g times pi over 4 for some historical reasons. And when you take different c, you get different values of g, pi, and 4. Well, no, pi and 4 have the same value, but g has different values. It sort of makes sense. You always think that things like that, they are kind of stretch invariant, but here we fixed how much the height changes when we do one step. So there is this length fixed in, so different g will have different models. So the analog we all love very much is that random walk graph converges to Brownian motion graph. And basically, it's a two-dimensional analog of the same thing, and the only difference that Brownian motion is almost surely continuous, and here we have almost surely a C1 class distribution. So those are the questions which, well, at the time when I read papers of Nijs and Nienhuis, and there are later papers by Hardy and many other people, so the questions which arise are how come very different models are all mapped on the same Gaussian free field? Well, there is a parameter, but still. So those models and CFTs, they have different central charges which go continuously from -2 to 1. And JFF normally you say that it's a field with central charge 1. How come they are mapped? And to these two questions, there were some answers in literature which I didn't feel comfortable with. Now, Coulomb-Gass approach has worked so far in all these papers only on torus or cylinder. And the question is again these boundary conditions. How do you do boundary conditions? There is one way in FK model, there is another way in 6-vertex model, and they doesn't quite fit with the complex loop model. So what to do with the boundary? And it's where does the imaginary part go and come from? Because we started with a complex thing, then suddenly it's real, then we pass to limit, it's again complex. So it's kind of, you know, you put rabbit in a hat, a frog jumps out, then you put it back, and again rabbit goes out. What does happen inside the hat? How to relate Coulomb-Gass to SLE, etc. So it's actually okay. So I discussed this with Rick and Scott and Wendell in 2007 in Park City. So 18 years. Wow. And it was sort of clear at that time what should be, for example, the boundary conditions, because we could, even back then, describe all the couplings of JFF with the SLE. That's continuous part is not story, and not a difficult story. And you get this kind of, well, you see them later, Pre-Schwarzen or Pre-Schwarzen boundary conditions, but then how the hell do I get a Schwarzen on a lattice? So it's first these things then appeared in the imaginary geometry of Scott, and then there were this long series of papers of Scott and Jason and Gwynne and Wendelin, but not in this thing. Well, the last but not least, how to make it rigorous. So I know, I think now answers to 5 out of the 6 questions. You can guess which one is missing. Yeah, if someone has an answer, you should well, unless you have I'm talking not to the 7 people who already heard this talk, 8 people who already heard this talk, but to others. If you have answered to one of these questions, you should speak now and not wait till the end of the talk. Okay, good. So off we go. So now, Coulomb-Gass some years later, so what I will try to do is to explain this, and I thought about it, well, not non-continuously for 18 years, but I had eventually a few kind of breaks, and a year ago I thought that I can do it rigorously, but apparently there are some things which are more complicated than the things I can do. And we'll start with a sort of mixture of some old and recent work. So what we want to do some conformal invariance. We want to capture conformal models of the domain. So we need some puncture inside to have non-trivial models. So what we do, we puncture point Z inside, and I want to study height or something around it. And of course, the easiest thing we can do, so suppose Z lies on a curve which goes from boundary to boundary, we can just say that there is one source on the boundary, there is one sink on the boundary, so there are these Dobrushin boundary conditions, which we love very much because they produce one silly curve, and the water flows, and then you ask what the chance that the water will flow through Z. Now, this is already problematic, because maybe it flows through Z in some loop. So how distinguish loop from this thing? So one thing you can do, you can revert half of it. So you put two sources on the boundary, which produce 1 gallon per minute, and you put a sink in the middle, which flows 2 gallons per minute. And then it's quite easy if you do these boundary conditions at a puncture in the border, well, clearly it has to come to Z. Well, if it's a proper plumbing, nothing disappears on the way. So there is an interesting thing here, that there is a height monodrome at Z. So it's something which you cannot see here in the Alps. There is a point that you walk around it, and you are 2 meters at a 2 meters higher altitude than you were before, because you cruise two lines. So it's not a genuine geographic map. There is one point where you have a disorder operator where the height changes by +2. But that's what makes it interesting. Okay, so how do complex analysts usually resolve this? So we usually do a crosscut. So for example, what you can do this green line, which should be a double line, which changes the height by 2 meters, and now it's all legitimate again. So you can think that there is this spiraling thing, which is now when you go around 2 meters higher, but here you just say that it's 2 meters high exactly along this line. But if you remember your complex analysis Riemann surfaces course, it's very important how you put this crosscut. So most things I will be doing will be crosscut independent, but at some points it's important to know how it goes. So you can just think that it's there, but for some calculations you need to know where it is. Okay, so this is what we're going to do. And then let's change the weights for the red curve. So we weighted not by nu inverse, but we introduce additional factor lambda, so it's lambda nu and lambda nu inverse. And then what we can do, we can try to find some Cauchy-Riemann equation around a placket. So what we want Cauchy-Riemann equation around placket, or, well, whatever, if you want Kirchhoff equations, if you don't like complex numbers, so in Cauchy-Riemann form, it would be the sum with coefficients 1, I minus 1 minus I around the placket. And how we're going to prove that? It should be rather general. So we should be able to prove it by rearranging just this placket, not going far away. Because bijections far away are complicated. They might depend on boundary conditions. So maybe you do some bijection by changing the direction of some loop. But what if it is not a loop, it touches the boundary or a Riemann surface, etc., etc. So we do bijections of this type. So you see there are quite several you can do. So basically you see that for any picture, so global picture would look like from two pluses, things come to this placket, and then there is another loop. You will see that there are, if you are a good plumber, you will see 4 different ways to connect this inside the placket. And the weights are quite clear, because the weights outside don't change, and you have full control over the weights in the placket. So those are the weights you get in these 3 vertices. So the bottom vertex, there are 2 possibilities. And then for Cauchy-Riemann equations, you need to solve this equation in factors. So there are 2 solutions, either lambda squared minus I nu minus 2, lambda squared is I nu squared. And the first solution is not interesting, because that you get by just moving along the interface this sink point. You don't use other reconnections. So the second one is interesting. And basically that's the lemma, that the function which we defined, f of z minus a plus b plus, so a plus and b plus are sources and z minus is a sink, it satisfies one of the 2 Cauchy-Riemann equations if you assume that lambda squared is minus I nu squared. Lambda, so this is, so you weighted, well, actually, we won't use lambda anymore, but lambda is the weight of the red things. So the water which flows in circle has weight nu. The water which flows from sources to the sink has weight lambda nu. So that's the difference. Okay, that's the lemma. So this is what was going for the FK Ising model, and in FK Ising model then it was observed that you there is a miracle that there is a second relation and you have complete analyticity and everything works nicely. So if you ask a physicist why Ising model is nicer than our other models, he say, well, Ising model is a free fermion. Or if you ask a person who does dimensions, then Ising model is a determinant or a Pfeifen. So it's, well, Pfeifen, well, okay, Pfeifen is nice, or determinant is nicer than determinant to the power 1/3, that sort of thing. Oh, okay. Now, what I'm going to do, and I was doing this originally for Ising model, but at the time everyone found it so confusing that I redid it with this Winnix. I'm going to rewrite this in terms of height function, because it turns out that this is correct, albeit more confusing way to do. So what we notice that actually in this picture number of red terms is just 4 times the height function evaluated at z. Now, if I want to evaluate height function at z, I need a crosscut. Because without a crosscut, it's not well defined. So let's do vertical crosscut. Suppose that a height function is 0 on the bottom. Then just below z, it's also 0 because loops don't change it. Above z, it would be plus minus 1, depending whether you're left or right of the green swan. So it basically would be that it is 0 everywhere here. It is minus 1 here, plus 1 here. Now, suppose that I rotated, made one full turn before arriving to h. So if h is, before arriving to z, if h is 0 here, to arrive to z, first I have to cross a curve incoming from the left, then curve incoming from the right, so h goes by plus 2. So basically every full turn of left curve gives h plus 1, but full turn of left curve comes with a full turn of right curve, which also gives h plus 1. So 720-degree worth of turns, they give me h plus 2. So basically the way to which we had lambda to the power number of turns is just lambda to the power 4 times h. So for example, on the left picture, 0 turns, h is equal to 0. Lambda to the power 0 is equal to lambda to the power 0. On the right picture, you have 8 turns, so lambda to the power 8 is equal to lambda to the power 4 times h equal 2. Also lambda to the power 8. And for simplicity, we can denote lambda to the power 4 by rho. So it's just rho to the power h. So we can just redo the same thing. Now, remember the lemma, it was written that lambda is equal to lambda squared is minus I nu squared. So rho is lambda to the power 4, it's minus I nu squared to squared. So minus nu to the power 4 was just minus mu. So this is from the old formula. So the mu, you remember, yeah, maybe I should just write it in big yellow letters here that basically n, well, square root of q, as people often write, is equal to mu plus mu inverse. And in this particular case, what we have is that minus mu is equal to rho. Okay. So basically, the lemma, I'm not going to prove it because it's basically the same proof, but one has to be careful. I found it's very confusing to work with monodromies because whenever you do calculation, you should fix a crosscut, but then you move a point and you should think how the crosscut moves, and it's really not very amusing. But basically, the function f of z minus, which is sum of rho to the power h, where is sum of all configurations monodromy z, satisfies these Cauchy-Riemann equations. So this is not entirely new. People were looking in physics literature at these things. So it's a combination of electric and magnetic operator. One of them is doing the disorder, and the another putting rho to the power h. But we will have a slightly different viewpoint on that. So a few important remarks that h of z is defined up to a monodromy z. We need a crosscut. So to probe height function there, you need a crosscut. So for example, this lemma, it means that you should define a canonical version of the crosscut to do that. For example, all going down, and then you have to check. Then the very same thing applies to two minuses going to a plus. Only you swap h to minus h. So instead of rho to the power h, should be rho to the power minus h, because you change the sign. But this setup, it changes only height near our point. So this setup, unlike the previous one, where you care how many curves are there, how many winding, whether they touch the boundary, doesn't care about that. You just have a small box height function in the box, you arrange the height function in the box. So it's true with any boundary conditions. It's actually true on a manifold with boundary, some Riemann surface. So it works with any boundary condition and any plus or minus operators. But again, it's a monogram. For example, if you do it on a Riemann surface, you need to do lots of crosscuts to make it all legit on a Riemann surface. So this is the general picture, that you have some number of pluses and minuses such that they all sum to 0, obviously, because we are nice, good plumbers. We don't want any unexpected fountains. So in this case, for example, there are 3 pluses and 2 minuses, and it works because the plus, what is inside, is counted double. So there are 2 pluses which are 1 gallon per minute on the boundary, 1 plus which is 2 gallons per minute inside, total of 4 gallons, and that 2 minuses compensate. Where there are crosscuts. And basically, the function which we can define, a multipoint function, is this, that you have rho to the power. We had height function with plus sign for minus point and minus signs for plus points. And it satisfies half of Cauchy-Riemann. And now let's check what happens if I take one point and I kind of rotate it around itself. So what do I mean? That I just cut out small neighborhood and twist it 360 degrees. Now the point where we probe the height will go around 360 degrees, so it will once pass through the green double line. So the height will change by a factor of 2. So it means that my h will change by a factor of 2. So it will be multiplied by minus rho, which is equal to mu by definition, this mu there. So you can write it, it's a unitary number, e to the power minus sigma pi I. So by the way, so there are, as I said, there are 3 setups. There is this Nienhuis model, there is FK model, there is 6 vertex. There will be slightly different formulas for in these 3 cases. So here there is a quiz for n-8 people who haven't heard the talk. What is your guess as what would be the sigma for the spin for the Ising model? Any guesses? Sorry? 1 over what? 1 over 2. And the other guesses?
1 over square root of 2?
Well, that doesn't work like spin. So 1 over 2 is very logical. But if you check the formulas, it's actually 1 over 2 in FK setup, and in 6 vertex setup is 1 over 4. And that already, I mean, I described to a couple of friends' physicists, and they said, well, then what you are doing is wrong. It shouldn't be 1 over 4. And it doesn't mean that what I'm doing is wrong, but it just says that it's different from what was in the literature before. So if you do an FK setup, you have 1/2. In 6 vertex there is 1/4, and we'll see in a second why it makes a difference. So rotating around plus gives exactly the same thing. So you multiply this time by rho to the power 2, but the height changes by -2, not by -1. So it still gets the same factor, so it's the still spin, the same spin, so exactly the same thing. Now let's do another exercise. Okay, doesn't work. Let's do another exercise. Let's try to rotate one point around the other point. Because just one point, you don't really have a monodromy, because you can have a canonic crosscut for a point, and that's what's happening in Ising model FK paper. But suppose we rotate u minus over around v plus. 2 things happen. First, when u goes around v, it intersects the crosscut. And when it was intersecting its own crosscut, you had a factor r to the power -2. But now it's intersecting crosscut of opposite direction, so it's factor r squared. But also when u goes around v, v intersects crosscut of u. So you have 2 points, each with a crosscut dangling down. So you intersect this one, but also your crosscut intersects this point. So you have 2 factors of rho squared. You have 2 factors of rho squared. So you have factor of rho to the power 4. So basically, what this means is that the first 2 observations, they mean that our thing is not a function, but it's a form of order sigma. So it behaves that when you rotate by 100 degrees, you multiply by e to the power 2 pi s sigma. So it behaves like du to the power sigma form. For example, if sigma is equal 1, it behaves like 1 form. If sigma equal 2, it behaves like quadratic differential. If sigma is equal 1/2, it behaves like square root of dz form. And the same for w. But when u and v approach, they should have also, first it should blow up, but also you should have a power 2 sigma because you have this monodromy which is twice the sigma monodromy. So this is like a simplest thing with the asymptotics of these 2 points and with the monodromy. So it's like a multivalued Green's function, if you wish. You could write exactly what it would be in the plane. If you want to write in domain, well, good luck, but you need to know boundary conditions. For some boundary conditions, it's really unpleasant to do that stuff. Okay, so why this is called Coulomb gas? It's called Coulomb gas is that if I write the partition function, so every 2 operators of the same sign, they go upstairs, and of opposite sign, they go downstairs. And what happens is that if 2 minus particles approach each other, then in denominator you will have 0. So probability of this configuration is very small. If they approach each other and the opposite sign, it blows up in the numerator. So it's more likely. So what you will see, sorry?
Never mind. You said denominator, but you meant.
When I meant numerator. Okay, I always confuse that too. Is there some mnemonic rule to remember? I confuse them also in Russian. Actually, I see no reason why they call that. Why don't we call them up-nator and down-nator, or whatever, yeah. Basically, it means that if you have a gas of particles, they will just kind of collapse fusion into pairs. And then the interesting thing that what you get is that in the end, you get logarithm of absolute value of f, which will be univalent. So all the monodromies will go into the imaginary part. And it will give exactly 2-dimensional Coulomb interaction, so 2-dimensional electrostatic interaction times 2 sigma. So it will be like perfectly nice, legit potential theory with no monodromy whatsoever. Okay. Now, what we do is, if we do fuse these 2 things. And this very much sort of relates to the paper we had with Clément Englert, and then which was later built upon by Chilcock and Englert and Izurov in various papers, is that if we fuse 2 points, for example, in this picture, take them nearby, what will happen is that we will retrieve the probability, more or less, that the curve will go through them. So we will retrieve the gradient of the height function, so the gradient of Gaussian free field. Yes?
If you have a plus and a minus inside, how do you know that they
Oh, they don't know. They can be on a loop also. They can be on a loop, yeah. You have slightly different conditions. One has to carefully work through that. But we are not working in this setup. We're not working with loop. We're working with 6-vertex model. So we don't care about loops. We just retrieve gradient of height function. This is just for illustrative purposes and to confuse Rick, this picture. Yeah, I should have made a 6. No, but I would. Okay. So basically, what happens if you fuse a plus and minus separator on an edge? You can fuse them in 2 ways. Minus comes from the left, plus comes from the right. And this is basically like a normal edge, but forced to go in this direction. If you fuse them in the opposite direction, it's an edge going to the right. So how do you fuse them? You do d-bar calculations on the left and move minus, and you fuse them in one direction. You do d-bar calculations on the right and move minus. You have arrow in another direction. And Clément and I did this for the energy density for the Ising model. And what was the difference with what I'm doing now? The difference was very easy. I think I forgot to say it. But the difference was that in that setup, sigma was equal to 1/2. So we were dividing by u minus w to the power twice 1/2 to the power 1. So there is no monodromy when you deal with fermions. So if you move fermion around a fermion, there is no monodromy because each of them gives like 1/2 spin, and that kind of cancels out. But now what we are doing, for example, if we do the same thing now for Ising, you have 1/4 plus 1/4, so there is 1/2 monodromy when you move them around, so you get different result of the calculation in this case. Okay. Now let me maybe say a few words about what I can do. I would be very much grateful if someone can help me with figuring out the second relation. So what happens here is that you have a function which has Cauchy-Riemann in U, Cauchy-Riemann in W, and you fuse them. And if you fuse function which is Cauchy-Riemann, well, say divergence-free in one coordinate, divergence-free in another coordinate, then on diagonal it should be also divergence-free. Unfortunately, it's not that easy here for two reasons. First, we deal with discrete function, and it creates complication. And second, it has monodrom, which creates yet another complication, and it's very easy to get lost. But you still get additional information from it being divergence-free in U and divergence-free in V when you fuse them. But when you fuse them, as I said, you retrieve gradient of height function. And gradient is always curve-free. So when you fuse them, you automatically have it being curve-free, being a gradient of something, but you also have some descendant of the other relation. But I unfortunately, so if someone helps me figure it out, I'll be very happy. I had a burned out of writing this monodromies over and over again. Okay, but now I made these words about Pre-Schwarz boundary conditions, so I should maybe do some calculation to kind of really intimidate you. So first, like a few words about covariance in complex analysis. So suppose F is a conformal map. So here are all the covariances you can possibly see in complex analysis in this list. And if you ask my advisor, Nick Makarov, does he know that? He says, you can find it in any book. And then you ask, where is this any book? I said, don't you understand? It's any book. And so there is this any book, which he has in his office. It's a big, I don't know, yellow book or blue book. I don't know where everything is there. But it's kind of a folklore knowledge. So first you can have invariant functions. So for example, solution to the Dirichlet problem for Laplacian is invariant. If you have harmonic function with some boundary values, you move boundary values. So Dirichlet problem, you get just its image. Now you can have covariant forms like du to the power sigma. So how do you get them? So for example, if you have invariant function and you take differential, you get du invariant thing. So for example, length element, like Poincaré metric. If you differentiate twice, you get quadratic differential. If you, what was in the FK Ising paper is power 1/2. And basically, I don't think, wait a second, I thought I had it written in this slide. No, I don't. But basically, the first corresponds to the Dirichlet boundary condition, and the second corresponds to Riemann-Hilbert boundary condition. So for example, if you say that your function on the boundary is proportional to square root of tangent vector, then you get the second option with sigma equal to 1/2. Okay, now the three more are Schwarzen forms, which are quadratic forms, Pre-Schwarzen forms, which are order 1 forms, and the Pre-Schwarzen form, which is just invariant functions. Apparently, there are three cases where you can have a quadratic differential, so it's du squared form, or du form, or just a normal function. And this should correspond to the height, to gradient of height, to stress energy tether. So you can check that if you add alpha log phi prime, where phi is our map, then this will satisfy the chain rule. And this is actually the martingales we see in the imaginary geometry. And Pre-Schwarzen form, well, if you have the first one, you can differentiate it and you get this. So you have this logarithmic derivative. Oh, wait a second, I have a typo. Oh, that's unforgivable. It's phi prime prime over phi prime, not the other way around. Sorry. Yeah. Okay. And then you can differentiate it another time, and that doesn't work out. It completely breaks, but if you are clever, there is a way to tweak it, and then you get this thing with the Schwarzen. So it's where Schwarzen is this thing. So maybe the important thing to understand is that the log phi prime, it's equal to 0 if you have what? If you have translation. If you take z plus constant, it's, then log phi prime derivative will be 0. Now, the Pre-Schwarzen form, phi prime prime over phi prime, will be 0 if you have linear map. And Schwarzen will be 0 if you have Möbius transformations. So in a sense, these three forms, log phi prime prime over phi prime, and Schwarzen, they measure how far phi is from translation, linear map, or a Möbius transformation. Okay. Now, a very simple conclusion to intimidate all of you. suppose we have the simplest possible f for the Ising model. It's meaning that we have a disk, no sources or sinks on the boundary, but just one source and sink inside. And the spin is 1/4. So I make an assumption here, it's kind of oversimplification, that phi is a map to a disk, and you have this formula. Like upstairs is the simplest thing which has this asymptotics. Now we put u equal to v plus epsilon, send the epsilon to 0, and we do expansions for phi prime and phi, and you do this expansion, you, well, calculate and calculate and calculate, and for simplicity I denote by, oops, well, okay, some doesn't work, crap, yeah. I denote a phi prime over phi prime, b phi prime prime over phi prime, and then basically you see immediately that, well, this is just expansion, then it's much nicer in terms of a and b because they defined by phi prime. You open it up, and basically this is the result. So the result is that it's epsilon to the power minus 1/2 in front, which is not surprising given what we start with. The next term is 1, so the next term just captures the geometry of the plane. The next term with epsilon doesn't exist, it's because we have trivial boundary conditions, so the conformal models doesn't see anything of linear order. But the next term is 1/24 Schwarzian derivative of phi. And as we all know, the Ising model has central charge 1/2, and for stress energy tensor, you are supposed to have 1/12 of, no, C over 12 times Schwarzian, so you should have 1/24. Yeah, okay. So those were the questions I've started with, and here I'm trying to do some answers. So how come different models are all mapped onto GFF? Well, fusing parafermions with the monodromy gives a boson. So normally when you fuse two parafermions with a spin 1/3, you expect to get something 1/3 plus 1/3 is 2/3, not a boson. But here, you know, this monodromy, it's kind of, yeah, people would normally say that you change central charge here because of background charges or screening charges. So here, well, I don't know what's the appropriate word, monodromy charge, if you wish. So suppose that you have monodromy, which makes it like two turns returning to the same point. It's, to some approximation, as if living on a cone of 720 degrees. Now, function z on a cone of 720 degrees, it's like function square root of z on a cone of 360 degrees. So this monodromy, it kind of changes these parafermions to become fermions. And then you fuse them, you get a boson. But when you fuse them and both of them were branching, when you fuse, branching disappears. It kind of annihilates. So if you take square root of z minus u and you you have square root of it u square root at v, and when you fuse them, kind of square roots cancel out. Now, what happens with the Schwarzian? Well, GFF, you don't get just GFF. And you couldn't see this on a torus or on a cylinder. You get GFF with covariance rules which depend on central charge, or with boundary conditions, if you wish. So the mantra from complex energy is that boundary conditions and covariance rules are the same. Now, for parafermions, we have Riemann-Hilbert boundary conditions. But when we fuse them, instead of Riemann-Hilbert covariance, this du to the power sigma, we get pre-Schwarzian covariance for the next terms, and hence pre-Schwarzian conditions. But if you try to do them on discrete, you will be a bit lost because they are not really, well, you see something, but not very nicely. Now, imaginary part goes and comes as it wishes because it's a complex, intrinsically complex problem, complex covariance, complex boundary conditions. So for any given domain, you can reduce the real part, but then once you move it a little bit, imaginary part pops out. And relation to SLE, CLE, it's just coupling with pre-Schwarzian boundary conditions. And how it make it rigorous, just work harder. Well, that's advice to me and all of us. I will be very happy to hear some advices about that. And in particular, you know, it's even in potential theory, this kind of monodromy functions, they are not very common. I asked, well, Makarov obviously knows everything. I asked Leonard. Leonard said that he only heard about it from Carleman. And, well, OK, I can't ask Carleman anymore, unfortunately. But I don't see any in the literature. So these are more or less the same things. Some new and old things take place. So there are discrete complex structures which are nice. There are green functions and fields with monodromies, which it seems to be new in physics and math. Then these fusing parafermions with monodromies gives a boson and pre-Schwarzian form. imaginary part, etc. And happy birthday, Rick. I was looking yesterday for a picture. The only one I found was, can you guess where it is from? So that's Ascona conference. So if you, so I'm sitting here, Wendell is staying there. Behind you is John Carney. So it's, yeah, it was, what was it, 15 years ago? Wow. And I just realized I want to bring a birthday present, but I forgot it. So there are actually tabletop games which do this. So there are two, which is called Tantrix and Trax. Have you seen them? Do you have them?
I don't have them, but I've seen the Tantrix one.
Which one do you want out of those two? Square one or hex one? You have to choose, and then I'll mail you. Maybe the positive thing, you don't have to leg it back.
I like the square one.
You like the square one? Okay, so you'll get the square one. Happy birthday.